There's a tool that's literally revolutionising design. Models that used to take months to make now take just a few days. Prototypes can be tested within hours of leaving a virtual world. And the previously impossible can be manufactured with ease. The simple fact is, whatever you're designing, computer-aided manufacturing has a part to play. Welcome to the props department at Shepperton Studios near London. Just one of the many places where computer numeric control, or CNC, is having a dramatic impact. In these tiny studios, they can make almost anything, from the magic watch used in the film Sleepy Hollow to an entire village, or even some rather futuristic weapons.
These were recently done for a film called Blade 2, a Wesley Snipes vampire horror film. And these are an implant that go on the side of the head. Tiernan actually drew these up on the CNC, because inside we had to actually fit 4 of these little blades, which also had CNC bits on the side, which actually fired out. So it all works on a syringe plunge mechanism, that when you press the plunger, the little claws come out and stay on someone's head. So the actual gadget then went on the side of the head like this, with the little claws coming out of it. So you'll see those in Blade 2.
When they're not trying to come up with devices for cyber cops, Shepperton's prop makers spend much of their time working on industrial models. From cars to kettles and buildings, these so-called aesthetic prototypes play a vital role in industry. They allow architects, designers or potential buyers to get an idea of how the product or development will look and feel before the real thing is finished.
And they want this. This is an old building. This is the new part over here which is being built. This is the acoustic theatre. And because of relative heights, they like to put on, if there is an off-site nearby, they like to make the off-site to compare heights and styles. Otherwise, someone can't relate the new building to anything. It's just something out of the blue.
Traditionally, models like these would have been made by hand. But with thousands of pieces, the more complex ones would take months or even years to complete. Computer-aided design and manufacturing, or CAD and CAM for short, have reduced the time it takes to make aesthetic prototypes to 1/5 of what it used to be.
We're working on a model down in London, and it's a dockside development. And it's got 8 large tower blocks on it. And it's quite complex, and trying to just fathom out how it goes is the problem as much as anything else.
The first step is to take the architect's drawings and turn them into a computer model. To do this, every detail of the plan has to be measured and then entered into the CAD package.
So we've worked around the front of the building. We're now onto the side elevation. It's suited well for CAD because the blocks all copy each other. They're all just repeats. And this section here, we need basically 16 of them. So I'm just going to set this out.
Entering the data might seem like a laborious process, but in a complex model like this one, many of the pieces are identical. So rather than having to draw each one by hand, they can simply be copied inside the CAD package. But the real time saving comes when you need to cut the pieces out.
It would have all been drawn up on a drawing board, because we'd have still had to redraw it up to make sure that everything worked. And then it would have all been marked out on perspex or marked out on plastic, and fret sawed, bandsawed and sanded, and just cut out manually. And it wouldn't have been as accurate, and it would have taken probably 4 or 5 times as long to produce the model. So it's quite a development, really.
These days, it's a very different story.
Right, there's the programme, just having a quick look on this machine, make sure it's coming into what we want.
Data from the CAD package is converted into code and fed into another computer which controls a CAM machine.
We actually have to convert that again into something the machine understands. And then we'll cut. Right, and just watch it for a while normally, just to make sure it's looking happy.
The code is used to control the movements of the revolving cutter. Each line of code contains X, Y and Z coordinates. These move the cutter backwards, forwards, sideways and up and down, so that it exactly reproduces the pieces drawn up in the CAD package. Here it's engraving the windows, a job that would be extremely tricky to do by hand. The other advantage is that once the machine's running, it can be left alone.
While the machine's cutting, you're getting on with drawing up the next bit, so you're not actually waiting for anything. So the minute the button's pushed and the machine is cutting, it's done really, as far as you're concerned.
Engraving 400 windows on the Perspex takes just half an hour. The next step is to tell the machine to cut the pieces out, but this means changing the cutting tool. CAM machines have a vast number of tools, sometimes called end mills. General machining tools fall into three main categories. Ball nose with a rounded end, used for general cutting. Flat nose with a square profile, used mainly for square edging. And facers, designed for use on flat surfaces. There are also a number of specialist tools, such as engravers, as well as bits that have been specially designed for high-speed wood routing, or for use with resins and plastics. In this case, a 0.5 mm engraving tool has been changed to a 2 mm ball nose cutter. With the right tool in place, the machine will do the work for you.
Well, this is the model that we've been working on the machine out there. These are all the floor plates for these tower blocks, and David is assembling all the elevations that we've been machining out.
Each model is finished and assembled by hand. Every piece has to be filed, cleaned and measured to make sure it's to scale. The designers constantly refer back to the architect's plans and make minor adjustments as they go along. The CAM revolution not only means the whole process is much quicker, it's also allowed model makers to produce ever more complex designs. But model makers aren't the only ones to have benefited. For generations, guitar makers face two simple problems. First, design a guitar that gives you the sound you're looking for, and then try and make some similar ones by hand. CAD-CAM not only means that replicas can be made quickly and easily, it even allows you to design your very own guitar.
It's the kind of guitar that was really developed in America from the 20s on. And I wanted to design a guitar that would have that classic look of a guitar from that era, with the sunburst and everything, but to have the actual outlines and the shape of the guitar to be contemporary.
Traditionally, the finest guitars were all handmade. The result is that each one sounds slightly different to the next. Whilst some players like this feature, Martin wanted to produce a small number of high-quality guitars with a similar sound. And to do that, he needed some help.
He wanted a guitar which was his, that he'd had a big input in. And he had some fairly radical ideas. And so we talked on the telephone, and he said, right, okay, I'll come up. And he did. And we kind of took it, from there, really.
Mike Vanden's one of the world's top jazz guitar makers. But what sets him apart from most of the competition is that he's one of the few who uses CAM technology. Armed with Martin's design brief and his own expertise, Mike began by creating a three-dimensional CAD model of the new guitar.
Okay.
The first step was to produce the general outline of the shape and profile, called a wire frame.
Quite a while. I don't know whether you can see this, but it looks like just 2D at the moment, but I'll try and rotate that, and you should be able to see that it's actually in 3 dimensions.
Having completed the wire frame, the next step was to see how smooth the surfaces were. By simulating different kinds of light and reflection, the surfacing tool allows Mike to see if there are any imperfections which need correcting. Only when he's removed all the imperfections in the virtual model will he begin inputting the settings for the CAM machine. At this stage he creates a 0 point. This gives the machine a baseline to work from, enabling it to identify any point on the virtual model and cut the shape of the raw material accordingly.
Okay.
The next step is to pick a suitable tool.
Now we want to select a tool. Now because we're machining curved surfaces, we'll probably need to go to, well, I use a bullnose which has got a radius on the corner so that it doesn't dig into the surface.
All that remains is to decide the direction of the cut or the tool path. This is particularly important when working with materials that can tear.
In wood, it's better to cut across the grain, there's less tearing. So we can specify that by saying cut at 90 degrees to the centre line.
Once these settings have been entered, the computer simulates the tool paths.
Right. So that shows us what the part's going to look like when we're machining it, and if there's any obvious mistakes. That's so far so good.
This allows any errors to be corrected without wasting expensive raw materials.
And this is a useful thing to have, you know, because you can really tell if you've written the program okay. Again, it saves time. It's much quicker to do it on here than set it up on the machine and find it's not doing what it's supposed to do.
The next step is to start physically cutting out the guitar. Unlike most people, computerized milling machines do exactly what they're told. So whilst the computer simulation can tell you if there are any problems with the toolpaths, it's vital to make sure the machine is set up properly before it starts cutting. First, make sure whatever you're cutting is held firmly in place, facing in the right direction. For large projects, it's a good idea to check the alignment by running the machine along the main axis and making precise adjustments if necessary. Next, make sure the tool in the machine is the one you specified on the computer. It may sound obvious, but it's an easy mistake to make. Now, line up the machine so it's directly above the 0 point you've marked on the block of material to be cut. When zeroing the height, use a feeler gauge to make fine adjustments. You're ready to cut, but before you turn the machine on, make sure you know where the emergency stop button is, and if there's a safety cover, this should be closed. The great advantage of CAM is that once it's running, the machine does all the work. So in the 2 hours it takes to cut out the guitar face, Mike can get on with something else. Machining leaves tiny tool marks that have to be carefully removed. It takes about 2 weeks to produce all the parts for the guitar, a fraction of the time needed if the processes were done by hand. But for Martin, the real revolution is that he not only gets the guitar sound he wants, he can have as many identical sounding guitars as he needs. It's often said that goldfish have a memory which lasts just 3 seconds. Well, this may mean they can chat for hours about the weather, The downside is that they've absolutely no idea of how much CAM has changed the design of the filters and pumps which keep their ponds clean.
This product is a filter pump for domestic garden ponds. I don't know if you can pick up on this box here. Basically, the pump itself sits in the bottom of the pond, and its job is to pass water and debris, bits of leaf, bits of twig, bits of fish poo, up out of the pond into a filter system which removes all of that debris, and then the water is returned back into the pond. So basically its job is to keep the water in your pond clean and clear and healthy for the fish. Inside this cage is a pump unit, which comprises an electric motor and an impeller. This impeller is, if you like, the driving part of the pump. And what we're actually doing at the moment is developing a larger version for use in larger garden ponds. And so as part of that process, we need a more powerful motor, and we need a larger impeller that's capable of producing higher flow rates to suit those larger ponds.
For any company, developing new products means massive investment. But before they get to market, each new product has to be designed, prototyped, tested and manufactured. By using CAD-CAM, designers have been able to dramatically reduce the amount of time it takes to bring new products to market.
What we've basically been doing, we've been in contact with our motor supplier, and they've given us the dimensions of the core motor and some clues of what we need to do. So what we've done is we've actually constructed on the screen in 3 dimensions, and we've wrapped around, the actual purchase motor, which is one of these, and built the mouldings round it. We've then sort of constructed a new impeller, which is the part that actually pumps the water, and then around that the pump chamber, and that's the core, that's the key aspect of the design.
The impeller may look simple, but it's actually an extremely complex design. The number of blades, their shape, height and overall diameter all directly affect the volume and pressure of water that can be pumped by the motor. Make the impeller too big and the motor won't spin fast enough. Too small and it won't shift enough water.
We have a lot of experience of developing pumps over the years, almost by empirical development of our products, and we know that if we want to pump higher, if we increase the diameter of the blades, then it will tend to, the leading edge of the impeller, its speed increases, so it will generate more pressure. If we want to pump a greater volume of water, the length of the blades will increase, so we know the golden rules.
But even tiny changes can have a dramatic effect on performance. So the only way to be totally sure a design will work is to make a functional prototype and test it.
To produce functional prototypes that are accurate can be quite difficult to do using more traditional means of hand fabrication. And so using CAM, it actually allows us to take a design from our CAD system, take that electronic data and generate a machining program which can then control the CAM machine and actually machine a part which to all intents and purposes represents what the finished product will be.
CAD data is transferred to the CAM machine. Within a matter of seconds, the new impeller begins to take shape. Traditionally, these prototypes would have been made on lathes and hand-operated milling machines. The new process is a lot faster and more accurate. But these aren't the only benefits.
The difference or the beauty of the new machine is to make prototypes out of the correct materials, practically the same materials that we can actually use in production. So therefore the test results are a lot more accurate as to what we really want.
Plastics are divided into 2 categories. thermosetting plastics are formed by a chemical reaction and once created are permanently set. They include epoxy and polyester resin and polyurethane. They're used in techniques like stereolithography and vacuum casting. The disadvantage of thermosetting materials is that they tend to be brittle. So whilst they can be used for aesthetic prototypes like this vacuum cleaner part, they're not usually suitable for functional testing. The finished impellers will be made out of polypropylene, which belongs to the other category, thermoplastics. They have what's called a plastic memory. When heated, they soften and return to their original shape. They include nylon, polyvinyl chloride and polystyrene. Polypropylene is difficult to machine, so instead the testing department chose to use acrylonitrile butadiene styrene, or ABS for short. This has similar properties to polypropylene, but it's much easier to work with. After machining, each impeller is filed to remove marks and blemishes left by the tools. The next step is to test them. The impeller and motor are placed in a housing and then submerged in a tank of water. The motor is then attached to a meter that measures the amps and watts. Wattage is calculated by multiplying voltage by current measured in amps. It's a measure of how fast electrical energy is transferred into other forms of energy. In this case, it tells the tester if this version of the impeller is suitable for use with this motor.
We're actually aiming for the 250 watts, but it's actually at the moment around about 270, 280, so it's still quite high for what we needed. So we need to actually modify the impeller or the motor itself to get it down to 250.
The testers also need to know how fast the impeller is spinning. This tells them the water pressure that's being produced. To calculate the revolutions per minute, they put 4 marks on the impeller and use a strobe. In daylight, the marks appear as a blur, but by slowing the film down, it's possible to see what's happening. The strobe flashes on and off extremely quickly, illuminating each mark at a specific point in the rotation. By varying the speed of the strobe, it's possible to find a frequency where each of the 4 marks are lit up at exactly the same point in their rotation. When the tester finds this point, the marks will appear to be stationary. The speed of the strobe tells them how fast the impeller is revolving.
It's round about the mark that we're after. We're after 2,500 RPM, but the wattage is still quite high, so we have to do a bit of juggling.
After final modifications, the new model pumps begin long-term testing for reliability and performance. The fish in these tanks are probably unaware of the lengths that people are going to keep their environment clean. And with a memory of just 3 seconds, we can be pretty sure that the cam revolution has passed them by.